Log on, tune in, find out. Another good idea from Cambridge.
The Wednesday session of the conference. Our first speaker this morning is Bob Guralnik from the University of Southern California. He's talking about derangements in finite and algebraic groups.
Thank you for everybody for especially getting here so early, especially to my colleague, Eric Friedlander. I think this is the first time I've ever seen him at this hour of the morning. Noon is a bit early for him. So I also thank you for the organizers, Gerhard and Meinhof and Sasha, for organizing this entire term and for inviting me to participate and for inviting me to talk here. It's always a pleasure to be in Cambridge and at the Newton. So, and thanks for the great weather that we've had this whole time while I've been here as well. Yeah, I think I saw the forecast on Saturday. It's supposed to pour, so we've got great timing here. And I'd also like to thank actually Tracy Andrew, who's certainly not coming to the talk, but who's been at the Newton for a long time, I think 17 years, and is leaving at the end of next week. Probably most of you have seen her at some point. I've met her over the years, and she's been extremely helpful to me and to everybody here. And I'm sure the Newton's going to miss her quite a bit. So, all right, so I want to talk about derangements, and also, if I have time, to talk about base size. So these are problems in permutation group theory, and that come up naturally in the context mostly of finite groups, although there are interesting analogs for algebraic groups, and I'm going to sort of talk about that, and also the connection between what happens in the algebraic groups and what it tells you about what the answer should be in the finite groups, and helps you prove it as well. So what is a derangement? A derangement is just a fixed point free permutation. So we have a group G acting on omega, on some set omega, and just so I'll always assume my set has size bigger than 1. And so if you have an element G and G is a derangement, just means it has no fixed point. If there are no fixed points. And of course, one of the oldest theorems in group theory is that if you have a transitive finite group, there exist derangements. So most of the time, we'll assume that G is transitive. And let's pick the stabilizer of omega. And so to say the derangements are just the things that are not conjugate to a subgroup of GW. So let's let delta of G be the derangements, the set of derangements. So I'll assume the action. I really should put in omega here, but I'm going to just assume we know what the action is. It's a set of derangements. And so that's just the union. It's G, and then you throw away the union of the conjugates. So Jordan's theorem is just that the union of the conjugates of a proper finite subgroup of a finite group is not everything. That's a trivial counting argument. One of the oldest theorems, I'll start with this one. One of the oldest theorems in group theory, before groups were around, is the theorem of Montmartre. I think it's 1708 approximately anyway, which says that if you take Sn acting on its natural representation, then the proportion of derangements in Sn goes to 1 over E as n goes to infinity. It's an easy inclusion-exclusion argument. Montmartre did this in the context of there was a card game at the time that was popular, and you won if you got a derangement. So the question is what was the chance of winning? And Okay, so, but rather amazingly, the question is how many derangements are there, say, even in a finite group? It's clear in infinite groups there are counterexamples. There are no derangements, and I'll talk about that particularly for algebraic groups in a minute. But how many derangements there are? Well, Sayre made the observation the proportion is at least 1 over n factorial. Because you may as well assume the group's faithful. So it has size at most n factorial. There's at least 1. Sayre also has a very nice article in the bulletin of the AMS a few years ago where he talks about applications of the existence of fixed points in finite groups, transitive actions, and to nice applications in number theory, topology, curve theory, and so forth. And so I would suggest you look at that. It's quite nice. Okay, but it turns out you also want to know not more than there's just one sometimes. It has nice applications. I think when I gave my talk here during John Thompson's conference a few weeks ago, I mentioned some applications to maps on curves and varieties in terms of looking at the image of the set of rational points in terms of, and that can be described in terms of derangements. But so there's a theorem, and rather remarkably, not proved until 1993 by Cameron and Cohen, that says if G is transitive, finite group, so I'll always say n is the cardinality of my set. So the proportion of derangements is always bigger than or equal to 1 over n. So you just, Sayre was pretty close. You just remove the exclamation point, then you have the right answer. And on the other hand, you can get such examples with this if you take, and in fact, equality holds if and only if G is a Frobenius group of order n times n minus 1. So in particular, n has to be a prime power. So let me prove, let me give a very elementary proof of a slight generalization of this fact. I'm sure this is the easiest proof of the conference by far. But anyway, this is actually, it's a slight generalization of Cameron-Cohen, and also the argument is a little easier than Cameron-Cohen. I mean, it's the same basic idea. But so first we need a slight generalization of what's called Burnside's lemma, which is not Burnside's lemma, but which says that the average, if you have G acting transitively, the average, or G acting on a finite group acting on a set, that the average number of fixed points is the number of orbits. So the generalization of that is, let me just put it here, is that if G is a normal in A mod G cyclic, so to say generated by the coset AG, and that you have A acting on omega, implies that the average number of fixed points of an element in that coset is equal to the number of common AG orbits. And the proof is the same as Burnside's lemma, so I certainly won't prove that. But so when A is G, it's just Burnside's lemma. And so here's the proof. So G is, so we have, so now the theorem is that the average number, well, the number of derangements, so we have A and G both transitive in that same setup on omega. The number of derangements in the coset, well, let's put it this way, the proportion of derangements in the coset AG is bigger than or equal to the number of common orbits on omega cross omega divided by n. So if A is G, there are at least two common, minus 1, sorry. If A is G, there are at least two common orbits on omega across omega, namely the diagonal and everything else, at least one, So, I mean, all orbits are common, and there are at least two orbits. Of course, if it's doubly transitive, that's exactly what you got. Okay. So so in particular, it's bigger than or equal to 1 over n if A is G. So this implies that it's either 0. Okay, well, I'll state a corollary, which I won't prove it. So it implies that there are no derangements in this coset. Or greater than or equal to 1 over n, or the proportion is bigger than or equal to 1 over n. So if there's at least two common orbits, then you get 1 over n. If there's only one common orbit, which is the diagonal, that means there are no common orbits on the diagonal, then in fact you can show there aren't any derangements. In fact, it's equivalent to no derangements. So, and those are what are called exceptional permutation actions that come up. In fact, it turns out they have all sorts of applications. They're fairly rare, but okay. And so what's the proof of the theorem? You just write down this equation. You just look at this. So f, let me call it x. So f of x is the number of fixed points on omega. And I sum over all x in that coset. Well, on the one hand, this is bigger than or equal to n times the number of derangements. Because if it's not a derangement, this is negative. Sorry, less than or equal to. On the other hand, what's this? Well, this is the sum of, first of all, f squared. Well, that's the number of fixed points on omega across omega. So applying this lemma that I just said, that's equal to the order of g times, so f squared is the number of common orbits, AG orbits, on omega across omega. And then we have minus n plus 1 times f, but then by that same lemma, that's the number of common orbits on omega. Well, that's 1. So that's a minus n plus 1 plus n, so minus 1. And that's the proof. But it took them 100 years or so of permutation group theory to prove this, so rather remarkable. And it has all sorts of applications. In fact, the reason that people started looking at it was because people were looking at polynomial maps and maps on curves, and this came up, and so they were asking, what's going on with this? And so Cameron and Cohen finally proved it. Okay. Okay, so as I said, it's not always true it's not true for infinite groups. And of course, there's the obvious example if we think about it. If B is a Borel in our algebraic group G, then G is let's say just G is simple. I mean, obviously, there's a simple algebraic group. Then every element's in a Borel. So on the flag variety, every element has a fixed point. And in fact, and similarly, it's of course anything containing B, so for any parabolic. So on the other hand, in fact, though one has the following theorem. So suppose that G is simple algebraic group. H is a proper closed subgroup. And we take omega to be the coset space. If every element has a fixed point, this implies that either H is a parabololic subgroup or the characteristic is 2, H is disconnected, and let me lie slightly here, and let me just say essentially, because one can cook up other examples from this one. But for example, if you assume H is a maximal subgroup, then H is O2n contained in G equals sp2n, or H is A2 with the 2 on top contained in G2. And it's well known that every element of the symplectic group is conjugate to an element of the orthogonal group, so that's not so hard to prove. So you do get counterexamples, but not very many. So even though it looks, initially you think, wow, there's all these examples. Of course, for general infinite groups, it is a mess, but for algebraic groups, you're in pretty good shape. Of course, what happens, why does that not a contradiction to the finite case? What happens when you go to the symplectic group? Well, there's two forms of the orthogonal group. So what it tells you is that every element's in one or the other of the orthogonal groups over. In the finite case. So essentially what happens is, and most elements are in one, not the other. I mean, for example, for a semi-simple regular element. So roughly the proportion of derangements is a half for each of those. And in fact, what's useful also for the finite case is when are most elements not derangements? And so you can say that the set of derangements, again, G is simple, say simple algebraic group. Again, you can extend this. And delta G is dense in G if and only if, again, under the same hypothesis, H contains a maximal torus. Obviously, if it contains a maximal torus, it contains all semi-simple elements, the derangement, the complement is dense. One or the other, something like that. Okay, so most of the time, except for maximal rank subgroups, most elements are derangements in that. So anyway, so now let's go back to the finite case. And so there was a conjecture that was made independently by Nigel Boston and Anar Shalev. It said, suppose that G is a finite simple group. Acting transitively. Then there exists a constant, absolute constant delta with bigger than delta. So you can't, in a simple group action, the proportion of derangements can't be too small. And again, if you think of the algebraic group case, what you see is, well, this is generally true unless H contains the maximal torus. Those are the only counterexamples. Okay. Let me point out, it is fairly delicate. And there, I think, I'm not sure why he just assumed it was simple. Because the point is, if you might think, well, almost simple groups should still be true. Well, in fact, it's not. And so it's false for almost simple groups.
One delta for each simple group.
What?
If it is in the wrong order, you want the delta first.
Yes, right. There exists an absolute. Okay, right. The delta doesn't depend on G. There's an absolute delta. Doesn't. Okay. And this actually, where does the counterexample come from? Well, again, think of the algebraic group case. if you take your simple algebraic group extended by a Frobenius automorphism, then Lang's theorem tells you that every element in that coset, all elements in the coset of Frobenius are conjugate. So if you let the group act on Frobenius, on the conjugate class of Frobenius, you see that every element in that coset has a fixed point. In fact, a finite number of fixed points. The number of fixed points will be, in fact, the number of conjugate classes in the fixed points subgroup. And so that tells you in most, and in fact, so in most cosets, you have no derangements. All the derangements live inside the simple group. And that can happen in the finite case, the analog. In fact, so the example is take a G, say Q to the A with the Frobenius on top, where sigma is the Frobenius. And let's assume that A is prime, just to make life simple. And the order of it, and A is relatively prime to the order of GQ, which is the same as being relatively prime to the order of G to the QA. But so let me just put that in. Then it's not too hard to see that every element in the coset of sigma has a fixed point. Namely, if you take an element of order A, it certainly, in fact, will have a unique fixed point by Cela's theorem, essentially. And therefore, anything in that coset, you raise it to, it will contain a Cela subgroup, and so it will act on the fixed point of that element, which is unique, so it has that fixed point as well. So every element in this coset has, in fact, exactly one fixed point. So the proportion of derangements is less than 1 over A. And A can be as big as you want. It's any prime. There's infinitely many choices for your prime, so this goes to 0. Okay, so you can't, so when I mentioned this to him here, he said, oh, but I didn't make that conjecture. But I don't think he thought about it, so it was sort of lucky he didn't. But, okay, so in fact, this conjecture is now a theorem. Where's the eraser? There. So we'll just and this is joint work with Jason Fullman. And so I just want to say a little bit about how the proof goes, because it does, I mean, a simple groups are basically Chevrolet groups, so it's going to depend on looking at algebraic groups and seeing what happens. And the fact that we know what's going on in algebraic groups tells us sort of how to proceed. So, of course, well, for sporadic groups, this is not much of a theorem, since there's only finitely many possible permutation actions. And anyway, you can actually get a pretty good bound using gap or magma. So, we have the alternating symmetric groups. And now, in fact, the symmetric groups, it turns out that knowing the answer for symmetric groups tells you quite a bit about what happens for the algebraic groups, not surprisingly, perhaps. So the theorem for Sn, so if G is Sn or An, well, so this is a combination of various people, Dixon and Luchak-Pieber, and Diakonis, and Fullman and myself. So first of all, in this case, with let's put it this with finitely many exceptions, and probably 0 exceptions, but that would take a fair amount of work to actually check. So there's always, no matter what permutation action you take, at least a third of the elements are derangements. And you can't do too much better, because we saw you get 1 over E in the natural one. And moreover, if we take a sequence, delta of G goes to 1. So most of the time, almost everything's a derangement, unless the action, I'm being a little sloppy here, is on k sets for fixed k. Well, n goes to infinity. So if you take some sequence where n is increasing, then in fact, almost everything, eventually everything, the proportion of derangements is close to 1 as you want, unless you're acting on k sets, and k is fixed. When k is 1, we saw that you go to 1 over e. But in fact, you can see that this can't possibly go to 1 because the rank of the action on k sets is k plus 1. And by the theorem that I put before, that gives you an upper bound on the rank, on the proportion of derangements, because that's the number of common orbits. So it can't possibly, so if the rank is bounded, it can't possibly go to 1. But this says, in fact, that's the only obstruction for Sn or An. That's not a theorem in general, because in fact there is a counterexample to that. But you can still have the rank going to infinity, but still the proportion of derangements not tending to 1. OK, so well, the proof uses some statistics about permutations, which so the action on k sets one can analyze, although there's still some open questions there. The action on when your subgroup H is the stabilizer of some system of blocks. Luchek and Pieber analyzed this and got some nice results, and it does go to 1 in that case, although we still don't know the rate. And if you have another maximal subgroup, so then it's primitive, and the point is there aren't very many primitive subgroups. They're very small, typically, and they don't contain, there's lots of permutations that are not contained in any primitive subgroup. In fact, most things aren't, which is how one proves it, which is, in fact, exactly what that's saying. OK. So now we know the answer for Sn or An. What about for algebraic groups? I mean, for the finite Chevalley groups. So there's sort of two cases. So first of all, the bounded rank case. So now let's take G to be a simple Chevalley group. Actually, you can work. So there's a problem if it's almost simple, as I pointed out. But in fact, if you just stay in the inner diagonal group, then it's fine, too. Problem is with Frobenius. Actually, graph automorphisms cause a problem, too. But in a certain sense. But I mean, since they have bounded order, it's not going to affect the proportion of derangements much. But if you work in the inner diagonal cases, it's still OK. So, but anyway, so bounded rank. So the nice thing about bounded rank is that, in fact, then you can use some algebraic geometry, and just let the field size go to infinity and see and so you can describe things in terms of varieties and without too much trouble. So in that case, roughly the theorem is as follows in this case. So if you fix a type of group, fix a type of simple algebraic group, and let me exclude Suzuki and Ree for the time being. I mean, it's still fine, but in fact, it's much easier just to deal with them separately. Then the proportion, so we have G to the Q. We look at this on some action, on some omega. Then what we see is that as Q goes to infinity, either the proportion of derangements goes to 1, or basically we have a family where where omega is GQH mod HQ. So there's some algebraic group in the picture. You're taking, that's the isotropy group. And H contains the maximal torus. So it has the same rank. And in that case, what happens, and then the limit as q goes to infinity of the proportion of derangements goes to exactly what's going on in the Weil group. I mean, you have to be a little careful in the twisted case, but I mean, this is roughly what's going on. And so, of course, for classical groups, we're essentially in the symmetric group case. And so we have the result there, so we can apply it. The idea behind here is that, well, if q is going to infinity, almost every element is semi-simple regular. Semi-simple regular is in a unique maximal torus. And you sort of, the point is you look at, so the maximal tori are conjugacy classes are parametrized by the conjugacy classes in the Weil group. And it's sort of what proportion of those conjugacy classes hit H. So that's exactly it. So you just, it's just sort of using that general correspondence between a tori. So for example, in the orthogonal group inside the symplectic group in characteristic 2, half the maximal tori are in one form of the orthogonal group, the plus, and the other half are in the other. That's so you get a half in either of those cases. In any case, this is bounded away from 0 by the result. For fixed rank, of course, it doesn't matter. There's only finitely many groups. But when we go to the rank increasing. Okay, so what happens in, so now when the rank goes to infinity, then of course it's hard to use algebraic geometry. There should be a nice theory, but there isn't as far as I know. So you need some sort of replacement. Although it turns out that with a fair amount of effort, at least when q is big, so now let the rank go to infinity. So there's sort of two cases. So case 1 is when q is going to infinity as well. Well, it turns out you can still handle that case because when the problem is you need now to prove bounds that don't depend on the rank. So you can't just use algebraic geometry to say, oh, we have use dimension arguments or something. But so you can prove that the proportion of semi-simple regular elements in a Chevrolet group tends to 1 as q goes to infinity independently of the rank. So the proportion is 1 minus big O of 1 over q, where that constant does not depend on the rank. I mean, so that's the whole point. You have to prove that the constant doesn't depend on the rank. That's a result that Frank Lubeck and I proved. Of course, the nice thing about the rank going to infinity means we don't have to worry about exceptional groups. So we're really talking about classical groups now. So it's a variation on the argument above. It's still actually quite a lot of work. For example, the case that's the hardest is when you're looking at, say, a GLA wreath SB. So that will contain a maximal torus, but it still turns out the proportion of derangements goes to 1. So the problem is, of course, so it has the right number of conjugacy classes, but there's fusion. So it doesn't have that many conjugacy classes in the big group is what's going on. So, but that actually requires quite a bit of effort. And similarly, you can prove, for example, in the action on parabolics, it goes to, as q goes to infinity, it goes to the limit of the Weil group, acting on the cosets of the parabolic of the Weil group, independently of the rank. I mean, so we can use our result on symmetric groups. So if you're acting on k-spaces, for example, then it goes to a limit, the same limit as for the symmetric group as n goes to infinity. And if your k-space, the k is increasing, then the proportion of derangements goes to 1 as well. But you have to work to do this. And then the secondly is when q is fixed. and the rank's going to infinity. Now here, algebraic geometry is not going to help you anywhere. So you really have to work pretty hard in this case. So let me just mention a couple of the ideas that are in here, and then spend the last 10 minutes or so talking about base size. So there are a couple. So what goes on? So some ingredients that go into the proof are you need upper bounds on the number of constancy classes so G is a simple algebraic group. F is some Frobenius endomorphism. You're taking the fixed points. And let's say Q is the prime power associated to the Frobenius. OK, again, it's not too hard to see that the number of constancy classes is roughly Q to the rank of the ambient algebraic group. Although there are a couple of issues. The results in the literature were actually weaker than that, anything in there. And also, what happens when R goes to infinity? You want to get sort of uniform things. So in fact, that's what Jason and I did. So what we proved is that and again, C is an absolute constant, and explicit absolute constant, and actually pretty small, maybe less than 100 certainly. I mean, quite considerably less than 100. In most cases, much better than that. And of course, we know by Steinberg, the number of semi-simple classes is at least Q to the R and is exactly Q to the R if it's simply connected. So we have pretty good bounds. So that's one ingredient. And the second ingredient is a lower bound on the size of the centralizer. So it can't be too small. Now again, just by general nonsense, you can prove that it's at least Q minus 1 to the R. But if Q is 2, that doesn't tell you very much. So that's the problem. And so what we prove is that it's roughly, I'm lying slightly, like Q to the R, and then there's a log factor, log of something, which I can never remember. So it's not so far off from that. So if you put these two things together, what it tells you is that if the number of constancy classes of H is a bit smaller than the number of constancy classes in G, then you just take the union of all the constancy classes that intersect H, and this implies that the proportion of derangements is big. OK, well, now what are the ones where this fails? Namely, the ones where essentially it's coming from something containing a maximal torus, because then it will have the right number of constancy classes. So then you have to worry about fusion. So then you have to work quite hard. So let me just say, if K of H is approximately the same as K of G, well, then you have to work hard. And for example, the case of subspace actions is, Jason just sent me the latest draft of it. It's 55 pages long. So it's just sort of, again, the idea is to reduce it to Weyl groups still. I mean, the point is, even for Q fixed, you can say there are still a reasonable proportion of semi-simple regular elements. It certainly won't be close to 1, but it'll be bounded away from 0. So you use that and some other things. But OK. I should say the way one proves this, I mean, Wall, a long time ago, had exact formulas for the number of constancy classes in the classical groups. So you have an exact formula. Well, getting an inequality from an exact formula, especially one involving generating functions, is not so easy. And fortunately, my co-author is an expert in this. So, because certainly when I look at Wall's formula, I say, I don't know. What does that set tell you? It tells me nothing. But fortunately, Jason is an expert in these things, so we get very, very good bounds for that. Okay. So anyway, that conjecture is now a theorem. And so let me spend the last 10 or 15 minutes talking about base size. So now again, G is transitive on omega. I mean, again, you can define this even in the intransitive case. But so a base is a subset such that no element fixes omega 0 pointwise. So you want to find a small subset so that nothing fixes all the elements in that subset. And this comes up, for example, in computational group theory because you can determine whether two elements are equal, for example, in a permutation group by just testing whether they agree on the space size. Of course, you won't always have a small base. If you take Sn, the base size is n minus 1. So, however, the general philosophy is that aside from some sort of obvious cases like Sn acting on k sets, again, if k is small, then you're going to find elements in the symmetric group that on a small number of k sets, you can find a non-trivial element that fixes the set of k sets. So, and similarly for say SLN acting on k spaces. You'll need lots of elements, lots of k spaces to sort of distinguish things. But aside from those cases, basically subspace actions and k-set actions, the philosophy is, and it's a theorem now, is that if G is simple or almost simple, finite or algebraic group, then aside from natural actions, natural cases, the base size is small. And I think there's a theorem by Tim Burness and Martin Liebeck and Anosh Shalev where they prove something like 6 or 7, maybe 7, in all cases for all simple groups. I think there are no exceptions, in fact. But in fact, most of the time it's 2. There are very few cases where it's actually not 2. So we want, indeed, mostly 2. So Tim Burness and Jan Saxel and I have a project to classify those primitive permutation actions of almost simple groups in which the base size is not 2. And it turns out there aren't very many. Although, again, if you want to get a complete list of exceptions, it's certainly a lot of work. But what happens, let me just say, what happens in the algebraic group case and how is it related to the finite group case? So in the algebraic group case, it's actually a bit easier because it turns out, so if G is, say, a simple algebraic group, and H is the isotropic group set. Then it turns out that so there's a slightly stronger notion of base size. I mean, so in the finite case, you can say, well, how do I find a base, say, of size 2? Well, you can work very hard and try to produce 2 elements. Or you can say, I'll just pick 2 random elements. And in fact, most of the time, that works. So there's this notion of probabilistic base size. That is, you pick a random subset of that size that will be a base. And there are counterexamples where there is a difference between base size and probabilistic base size. But in fact, most of the proofs tend to prove probabilistic. The bases, you get this by just sort of picking a random set. And in the algebraic group case, what would that mean? it would mean that you take a random element, or you look at the set of elements G and G, such that H intersect H to the G is trivial, and that should be contain an open subvariety of the group. And it turns out that there's a very easy criterion for checking that, namely, so the point is, so G has sort of generic base size 2. If and only if for any let's say X and H, if you look at the set of V and omega such that some conjugate of X, some H conjugate of X fixes V, so in fact, one just has to check for a single conjugacy class of A. Let me take H to be alpha, to be reductive. Let's assume this is reductive. If it's not reductive, there's a variant of this. So you just have to check for a single element in H, look at all of the points that are fixed by some H conjugate. And either that's going to contain an open subvariety of omega, or if it's not, then it turns out that you'll have this property, that you'll be generically base 2. And moreover, this element X, you can always take it to be either a prime order, well, if you're in the positive characteristic case, you can always take it to be a prime order, because if it doesn't have prime order, just replace it by a power of itself. And in particular, either unipotent or semi-simple. And in fact, so there are two ingredients in proving this. I mean, there's a very easy algebraic geometry argument that tells you what's going on here, but the point is, if behind this is what's going on is, there are two cases. If the generic stabilizer, or if you take a point and its stabilizer has positive dimension, well, then either it contains a unipotent subgroup or it contains a torus. And if it contains a torus, you can always find an element of order either 2 or 3, depending on what your characteristic is, in the torus which fixes it. So the problem is, what if the isotropic group is finite? Well, then what you can prove pretty easily is that there's an upper bound on the size of the isotropic group, at least on an open subset. So there's going to be some n such that for an open subset of omega, the isotropic group will have order at most n. And that's just the fact that you have basically you have some degree n extension of a function field, and so you know that over a generic point, if there's only finitely many points above it, there's a bound on most of them, because at most places it's unramified on an open subvariety. It's unramified of degree n. So in fact, you only have to, once you figure out what that n is, you only have to worry about elements of order at most n. So there's only finite many conjugacy classes to worry about. And the other ingredient that comes in here is that the fact that if H is reductive subgroup of G, any conjugacy class of G intersect H is a finite union of conjugacy classes. So that comes in there, which basically follows from the finiteness of unipotent classes. Okay, so and moreover, again, if you have this set up, and now what happens if you look at G of Q on H of Q? So if you're generically base 2, then what it tells you is that that's equivalent to being probabilistically base 2 as Q goes to infinity. So as Q increases, that you take a random subset of size 2, that will be a base. On the other hand, there are examples where it's base 2 but not generically base 2. And let me give the example in the algebraic group case. And then the connection with the finite groups is a little complicated, but you know. So here's an example. So let's let G be a simple algebraic group. Characteristic not 2. Let's let tau be in the automorphism group of G an involution. Such that tau inverts a maximal torus. If tau's inner, then this determines it completely. If tau's outer, you have to choose one. Or there can be two different classes, but actually no, there still can't be. I think this determines it uniquely. So okay, then if you let G act on tau G, for example, then this is base 2, but not generically base 2. Okay, as I said, this is joint with Tim Burness and Jan Saxel. So, and why is that? Well, actually, I was trying to prove the opposite of this in this case, but I kept running into problems. So I figured I'd try to do the other one. So it turns out that this involution, in fact, turns out it inverts every conjugacy class. That is, if you take any element and apply tau to it, it's conjugate to its inverse. Think of the case of SLN transpose inverse. That, of course, it can be inner, for example, when there's no graph automorphism, it will be inner. And, okay, there's an old paper of Springer back from the 70s, which for some reason I was Googling. I couldn't find it on Math Science. I just Googled, and I don't even remember what I put in, and Springer's paper popped up. And he was looking at a regular unipotent element and sort of looking at, in the grading on the roots, where you had jumps in the centralized. And you can get it out of that. It turns out afterwards I came up with a different proof. But it turns out it also has the property that tau acts as inversion on the centralizer of a regular unipotent element. So it's going to invert a regular unipotent element. That's one thing. But in fact, it acts as inversion on the full centralizer as well. And okay, so I don't know if this was known or not. I had asked Janssen this, and he said he didn't know it, but he couldn't think of an application for it. So I said, here's an application. So why does this imply that it's base 2? So you take, so we're acting on the isotropy group is the centralizer of tau. So what I do is I can take tau and a conjugate of tau to be this regular unipotent. And then the centralizer of tau intersect the centralizer of tau prime is 1. Because if something intersects both of these, then it centralizes the regular unipotent. But nothing that's centralizing the regular unipotent centralizes tau, because tau acts as inversion, and we're an odd characteristic, so there are no involutions. So this is 1, and that's exactly saying it's base size 2. This is the only regular orbit. Because if tau times tau prime is not a regular unipotent, well, if it's got a semi-simple part, then there will be an involution I mean, first of all, if the centralizer of this guy is not abelian, it can't possibly act as inversion. So this involution will centralize something in the centralizer. So this has to be abelian, which forces it to be regular. And it has to act as inversion, and it has to have no involutions. So there can't be a semi-simple part. So it has to be unipotent, and its centralizer has to be unipotent and abelian, and that forces it to be regular unipotent. And moreover, this is unique up to conjugacy. So there's one regular orbit. What happens generically? Generically, the product is regular semi-simple. The centralizer is a torus, so the intersection will be the involutions in the torus, so it'll have size 2 to the rank. So the generic point stabilizer, or stabilizer of 2 points, is finite, but non-trivial. But there is one orbit. So this shows that things are complicated. And let me stop here.
Thank you very much. Are there any questions? Yes.
Do you have some explicit value for this delta in your previous theorem on proportion of duration?
So yes. Well, yes and no. So the point is, we prove it as an asymptotic theorem. So with finitely many exceptions, I think the band we have at the moment is 0.03. The correct answer is probably something like a sixth, and maybe even better if you exclude, asymptotically it might be a third conceivably. Probably not quite that, but something on that order. So that comes out of the proof, but the problem is we don't want to do all of the, it would probably take about 10 times as many pages and probably the rest of our lives to actually, be explicit in all of the little cases. So for example, when the rank's going to infinity, we just, wave our hands and say, okay, do we really want to check all of the little cases? It's clearly not going to, in E8, well, it's probably not so bad to do it, but on the other hand, you have to do all of these cases.
Do you have any value like 10 to the minus 10 or?
No. No. Well, I don't know. One might be able to get a proof out of this because, I think if you look at the estimates that we give, I think one could say if Q is bigger than something, we're okay. If the rank's bigger than something, so there's only finitely many cases to check, and then one could say, okay, what's the biggest possible order, and then 1 over n. So we could do that. So possibly it would be a horrible constant if you did that, but at least asymptotically, it's actually a reasonable number. It doesn't even get close to 0. But it's we thought about it, and then we decided we didn't want to work that hard, so we stopped.
Yes, Alex.
Is there any chance to replace to have result like that or similar results with replacement of G, order of G by the number of conjugacy classes, and that number and delta of G by the number of conjugacy classes with this property rather than number of elements?
Probably. In fact, that's sort of what we do, but we haven't kept track of that. But it's certainly plausible. Yeah.
That it could be closer look to that.
Yeah. No, that's an interesting question. It's just what proportion of conjugacy classes are derangements? That's actually a nice question.
Exist some similar business in case real. This notion of the arrangement, the
Derangements.
derangement, etc., etc.
Well, I'm not sure. I'm not sure what the analog would be.
No, I'm not sure.
Okay, well, thank you very much.